join me thanking the panel. And I think that they left a positive message for our closing speaker, which is going to tell us beyond the horizon, which links with your horizon. But let's welcome Andrew and thank the panel again. So good stuff. And it's not trivial to close Multicore World, so there is nothing like an experienced speaker to do that.
Okay, it's been a great week so far. It's been, had some really good time to connect and, meet some new friends and just really understand a lot from a lot of people I haven't known. So I did save kind of a personal story here for last. And so I'm an avid cyclist. So mountain biking is my preferred discipline, but I will get on the road bike and have a little bit of fun. This is a picture actually from now 15 years ago, so kind of coincides with the earthquake that was here. Group of us on top of Mont Ventoux. So it's a trip wife and I did, took about 2 weeks, followed the Tour de France, got to ride parts of the course. But the interesting connection here is we signed on with this tour group that does these things, and they had like 3 buses, right, that go around France, and in this case it was, parts of Italy, a little bit of Switzerland as well. And so we were the 2 Americans they put in the bus full of Aussies, Kiwis, and two from Tasmania. So we had just a great time. Yes, and that's a whole story too. Those poor Tasmanians took more grief than we did. But, we made some great friends. We still keep in touch with a few today. But I learned a lot about, All Blacks and Wallabies and the Springboks. And I don't know if it was a World Cup year, but it was intense, the rugby conversation. And I'm not a big drinker anyway, but that's the other thing I learned. Like, these people are absolutely insane, stay up till early hours of the morning. We'd hop on the bikes first thing in the morning, ride some god-awful elevation in miles, and it was like no big deal. So it was impressive, but it was a lot of fun. Okay, so we covered a lot of this in the fireside chat, but one of the things me and the team do every year is we put together a list of kind of trends that a lot of our senior leaders and senior technologists should be conversant in, or at least should be aware of. And we pull from IEEE, venture capitalist community, do a big internal survey. So we kind of scour a lot of the information sources to pull this together. And in fact, so we published this in the fall. In fact, we just started on the version of this for this year. So what I've got here are just kind of the top 5 that we shared out. And so I'll walk into a little bit of these just for awareness here, because I think it applies to a lot of the problems, kind of we were talking about this week. And one thing I'll say, there's a unifying theme across all of these, which is, and I mentioned this the other day as well, for a few years within this community, we've talked about the convergence of HPC, AI, data analytics, right? That was a theme. Maybe that was a multi-core world theme at one point. Maybe a good thing for next year, though, is now another plus sign, which is bringing in elements from public-private hybrid cloud, especially, so from the enterprise, from a technology perspective, not so much the economics, but it goes in line with, the Nogueira, Reed, and Gannon paper that we talked about. So the first one is this agentic enterprise. Anyone in their history, I know there's enough, kind of diversity here. Anybody do just, kind of old school enterprise IT administration? Was that ever part of your career or job? Yeah, okay, everyone maybe a little bit. So you'll remember some of this, right? It was, for us, it's been like a 20-year journey of, we call it the adaptive enterprise, or, converged infrastructure, hyperconverged, blades. There's this whole generation in enterprise. What it was really trying to do, though, is really optimize how you deploy, manage, and get high utilization out of networking, compute, storage, right? That's kind of that was the simple vision of it, and it still is today. So AI now is really seen as, well, maybe that's the missing tool. Maybe that's the missing piece that's really needed to bring all of this together, to make that a reality. So I've got a few examples that we're already kind of pushing forward on in this respect. But first here, this is a good one. So this is kind of a taxonomy. Normally, if I was just talking about agentic AI, we would just build out a presentation on that. But I'll make a couple of points. This is a good takeaway slide, and you'll have this one because it matches our internal taxonomy pretty good. From this timeline, kind of talks about, well, how do you go from just simple chatbots, and how do you get on this path to agents, and whether different levels of that. And it also talks about fit for use, where agents good, where they're not. But really, I'm going to draw your attention to the two numbers here. So this is Gartner, came out in August, study they had, said, okay, by 2035, so 10 years away, basically, 30% of enterprise application software, predicting that revenue is going to surpass $450 billion, okay? That right there is the answer to one of the first questions you asked, Nicholas, early in the week, which was, is this sustainable? What's the math behind everything? This is what's driving it, that number. And if you think that's real, some level of this investment and build out will continue, but it's all about the second number, which says, well, okay, over that time, 40% of these projects that get started are going to be canceled. Well, why is that? It's because, look, it's going to take a tremendous amount of trial and error to figure out what works, what's a fit, what doesn't. So, depending on how you turn the knobs on those two numbers will greatly, affect, look, does this spend continue or not? So measuring ROI is going to be critical. So I'm going to just spotlight a couple of projects that we have going right now just to show you how, at least I think some level of this is real. Will we achieve those numbers? I don't know, but we're already seeing pretty good success. So this first one is a platform that we, the labs team, helped develop with our operations group. So it's an agentic platform for support automation. And it doesn't sound glamorous, it doesn't sound exciting, but it has a massive ROI. Because the way it works is basically if you go to support.hpe.com, this is going to be the engine behind it. We've already got the first phase that's up and running, but literally, if you're a customer, comes in, you've got a problem, if you're not on some big service contract, this is going to be your path. And then even if you do have a service contract, our solution engineers are using the same console. And this platform is tied into all of the knowledge base, all of the Salesforce console, all of that. And so ultimately, it is an agentic model then that takes advantage of multiple LLMs. It's hitting all the different repositories that exist within the company and actually functions just like a real support engineer would work. It's not just a simple pipeline of, okay, dump a bunch of documents into an LLM and see what it gives you. There's actually a lot of reasoning that goes into it, and I'll say a couple of things about it. Another really cool feature of it is our services organization over the years. They've developed hundreds of these knowledge base graphs. And I know you've all had experience with these when you just call customer support for whatever widget you own. And we've all been there. We just want to scream at the other person. Like you can see the flow chart in your head. You could draw it out yourself and you say, look, take me straight to this point. I don't want to go through the, have you done A, B, C, D? But some of these decision trees in our case, are very complex. And so we've digitized about 400 of those at this point, and now that's part of the knowledge database that feeds this. So the model now is smart enough to know, based on the interaction, what's happening. It knows where to go in each of those decision trees as part of the answer here. So this is just, in its early build out, but we've got, several phases planned on this. Another term I'll drop on you for, additional study, and maybe we'll come back next year and talk more about it, is this concept of a virtual foundation model architecture. We call it an agentic OS. There's some other work going on that you'll see even at supercomputing or kind of out in the literature that talks about that. So if you do a look up on agentic OS, then you'll start to get a feel for what this is about. Okay, so now that's kind of at a big scale. Let's go a little closer to home. Talk about another model that's been developed, and this is one that is controlling the liquid cooling loop in our high-end AI and HPC supercomputers. So it started life as a plain reinforcement learning-based agent, and we had really good success with it. But then over time, we've done the same thing. We've implemented more of an agent-based approach on this as well, to the point where we can alter pump speeds and monitor set points and control set points, and we're seeing really good results on this from implemented it on Frontier. So that's the first system at Oak Ridge we've deployed this on and seen really good results. And then we took that, because it's part of a larger collaboration with Oak Ridge. It's called the Exadigit program, and so it's a full digital twin, or the intent is going to be a digital twin of Frontier as well as the facilities around it. So our liquid cooling based optimizer now is also part of that operation. And so we're going to get, and I'll talk a little bit more about some of the end-to-end savings you can get once you start putting multiple agents together. But well, I'll just move for brevity here. Okay, now this is kind of the crazy mad science end of things, and you might look at this, and the idea here is what we call a global cloud orchestrator. So really the question is, it's not about when you run a task or a workload, it's where you run it. So this is believe it or not, this is what's happening with the hyperscalers are headed this direction. We're going here to some degree with some of the private clouds that are hosted in colos across the world. But the fundamental idea is you're either following the sun or you're trying to take advantage of, okay, where's energy costs? Can I do energy pricing arbitrage? So where does it make sense to run that workload? Tons of complexity in this one. A lot of reasons why it won't work and why you've got to have the right situation. Really, the reason I bring it up is because there will be technology that comes out of this that I think will still apply to this community. Okay, it may be it may be just very simple things like, okay, Dan's got a cluster of CPU-based compute, and he's maybe getting ready to turn that off. It's pretty, utilization's pretty low on it. Maybe Jess just bought his new, quantum system, and they're going to do a little bit of trading or something. Even the DOE hub and spoke model, there will be things that come out of this that will apply in the long term. But that's kind of an extreme limit here of an optimizer that we're already seeing work on. Okay, so just a couple other examples we also have already in operation. Kind of mentioned, more at that enterprise, adaptive infrastructure. We call that GreenLake Intelligence. On our networking side, we have something we call an agentic AI mesh that's managing the operation of your network, both wired and wireless. And then on the lab side of things, I've got a couple QR codes here to some of the papers based on some of the work I just talked about. And this is, I'll leave this with you as well. So I don't have to get the cameras out just yet. Okay, next one, beyond the grid. So really this one, this is going to, really just kind of, probably underscore a lot of the points Dan's already made, or, things we've talked about. But I'll talk about a couple of trends and maybe give you a few more kind of fun data points here. So first chart here is tracking computational performance of AI supercomputers. So this is, we're just normalized at 16-bit at this point. So I've got a data point here with Frontier that launched in 2022, even though that's a 64-bit. The reason that's an interesting year is obviously that's also when ChatGPT, dropped their first model. And that's when we started getting the phone calls, from, we think we kind of need this thing that looks like a HPC supercomputer. Can you put more GPUs in it? And so I took a snapshot. This was in 25. And so this Colossus machine from Elon and team, that was kind of the high end at the time. So you can see kind of the trend line, 2.5x per year is the performance growth. Yeah. And it doesn't show obviously every system in China because, they probably have a few more up here as well. In fact, we know they do. Okay, so this is a fun one. I've got some fun. I did some, crunch some numbers here during the break. So power requirements. So performance is going at 2.5 a year. Powers, it turns out, is going about 2x per year. So Frontier came in 21 megawatts. The Colossus system, this time last year, phase 1, came in, it's 150 megawatts. So that was 100,000 H100s. And if they're not there yet, they're close to having doubled that at this point, okay? So here's all the information we had on the Grok 3 model. So I'll have some fun numbers for you on this one. Grok 4 actually launched about 6 months after this, but I've got all the data on Grok 3, so I decided to use that. So Grok 3 model, you can see how much training compute was needed. It took them 100 days to do the last epic, the last big training run on that. So if I crank the math out, let's see, who was, Dan, you were 7 cents a kilowatt hour, right? Okay, how's this for fun? So it's 7 cents kilowatt hour at 150 megawatts. That works out every 24 hours, your utility bill alone is $252K. That's $300,000, no, that's 420K New Zealand dollars, okay, per day, 24-hour run. So to do the entire, that 100-day training run, $25 million for Dan, it's going to be $42 million for you. And then Simon, I didn't forget about you. At 35 cents a kilowatt hour, oh my gosh, 1.2 million US, just under £1 million for you a day, just for the power bill. Train it, 100 million pounds. How's that? So those are some serious numbers. Another chart kind of goes to, Dan kind of mentioned this one as well. This was from a DOE report, and it'll be interesting to see if they update it this year, because they were predicting, data center as a percentage of U.S. total consumption, was, on that 10 to 12%. Last year we were seeing maybe doomsday scenarios that said 25%. Dan told us today 49%. So, yeah, that's true. That is their business. Yes. So it's real. Okay. So this one builds out. Maybe I'll just for the sake of time, I'll just go all the way through it. Forgot that. So this is really, this will be a slide we'll come back to next year even, because this really shows kind of the problem in solution space from the power side of things. And it shows kind of total data center energy flow, all the way from the feed or the input all the way to the output. And most of our time, most of my time as a computer architect has really been around optimizing number one. How do I get maximum productivity of the system? How do I increase utilization? How do we do liquid cooling, right? We do all of these kind of things. But when you look at it, so to really get good gains, of course, we need to improve there, but the opportunity is going to be across all 6 of these steps. And if you think about it, fundamentally, what's happening here at the data center level, well, you're sending power in, and really, what do you get out of it? You get transformation on data, you do some number crunching, and you get heat. That's about it. So the whole point is on each step, there will be opportunities, particularly applying some of the agentic AI to bring some increased efficiency, into this. And so you'll see things like, before the focus was all on PUE, that effectiveness, you'll start to see more and more around ITUE. So how much power really gets to the logic devices, how efficient are we there? So that's where, again, whether it's quantum, neuromorphic, analog, how can we be more power efficient on getting that compute? And then, as we've also talked about some here this week, once that heat leaves the building, that's kind of one of the beauties of liquid cooling especially, is, my heat transfer mechanisms I can be a lot more creative with, and we see things across the globe, really creative uses of that heat, whether it's melting ice on sidewalks, heating fish farms. I was at one forum, and it was the city manager of, I think it was Manassas in Virginia, which you might imagine, they're building out a lot of data centers. So they had a big public forum taking input, and citizens, they were there with the pitchforks and the signs, no more data centers. And it's like, look, we're not getting jobs out of this thing. There's nothing that's being added back to the community. What are you going to do for us? And at least in that particular case for that particular data center, they got a heated community pool out of it. So those are the kind of things you're starting to see. Okay, last point on this to kind of just reinforce that, are there things that we can learn from enterprise IT that we can apply here? And yeah, it turns out there's some really good parallels. If you look at kind of the history that we've done with IT and the degrees of automation, how in the early days it was all about reactive, and then, slowly but surely, we're trying to move up to this autonomous operation. So that's what this stair step shows. On the energy side, we can kind of do the same thing. So that's the idea, is what can we take at each step? What kind of innovation and advancements can we make, kind of following, similar process that the IT industry has used, and so how can we apply that to the energy sector and the energy problem? And I think for sake of time, I'll not jump into that one. So again, number of things that we've got in the works right now. On our enterprise side, this is another capability that we're bringing to HPC. We have something called the Sustainability Insight Center, and that's literally how you're going to be able to view and know. You got to have the metrics to know what you're consuming, and so that's a tool that gives visibility on that. And then on the lab side of things, kind of 3 big things we're working on right now, something called holistic power management, and then a lot of work in digital twins, and then this next generation grid. So I've got another QR code there for some follow-up. Okay, next one, I'm just going to really quickly flash this concept of proof before trust. And I think this one's especially important. Normally you wouldn't think, well, look, a lot of our HPC environments are, in some cases they're guarded with machine guns, so we're good. It's air-gapped, whatever. But as we see more and more, I think, AI governance and regulations come online, this is something we all need to be thinking about a little bit. So I'm just going to set up the problem and again, kind of tee up maybe for a follow-up what a solution looks like. So the problem as it exists today, we can do pretty good at a node level of ensuring that, look, when that node comes to you, we turn it on, we know the firmware that's on it is we've got a certificate for that, it's been authenticated, but there's a number of bad things that can happen once you let someone on your network, either privileged or otherwise. So today, from a physical access, we have technology. We're pretty good at protecting data that's at rest and in transit. Okay, so that's not so much the problem here. The big hole that we have right now, though, is when that data is in use, while it's actually being computed. And why is this becoming a larger problem? Because more and more, started on the enterprise, right? Coming from cloud environments, virtual machines, containers. So once you turn those loose and you've got a compromised insider or something malicious, look, they can look at all of that memory state. Doesn't matter what container it's in, what VM it's in. So we want to plug that hole. And so the concept here is something called confidential computing. And it's going to leverage something called a trusted execution environment. So this in part leverages capability that's available in Intel CPUs, AMD, ARM has capability. GPUs are kind of mixed right now where they're at on that, but the roadmaps are looking good. It's a fairly, I wouldn't say complicated, but anyway, the process to kind of walk you through how all the attestation steps work on this, it's probably another 10, 15-minute conversation. So I'm going to save that for another time. I really just wanted to kind of raise this as hey, you should kind of be thinking about this as you start to deploy more and more VMs and containers, even for HPC and AI workloads. Yeah.
Microkernel.
Let me see if I'll give you a sneak peek. How's that?
If you just asked if they use things like SEL4, the trusted microkernel, which, as an example.
No, it's using, I don't have the instructions listed. There's a core set of instructions in each processor. I want to say like SVX on one of them. I always get Intel and AMD confused. But this is basically the set of steps that it takes. What's not kind of shown here is kind of the instruction sets that you're actually leveraging, particularly for part of the, let's see where it's at.
Probably number 5.
Well, yeah, it's part of 5. Ultimately, you have to get a key from this signed measurement's kind of the key for the CPU. That's kind of the main thing you're looking for. And then so the process to get that signed measurement, that's kind of what it's all about. Okay? Okay, on to quantum. How are we doing on time? Not too bad. Okay. Okay, so quantum, the journey. Where have we been? Where are we going? Really today, what we can do today, small-scale simulation engines, large-scale starting to come online. We talked about that the other day. Somewhere around 50, low 50s qubits. That's about all we can do full fidelity simulation on right now. And so where this is going, I'll walk through some of this, is we're going to introduce a concept called adaptive circuit knitting. Eventually, we think the answer is this hybrid HPC quantum scaling. And then, years from now, maybe you get to your large-scale quantum. But I think if we're, again, intellectually honest here, there's a lot of work to do. So, okay, first thing I want to, kind of show as far as being intellectually honest is, the pace of development has not been good. So, some of my dots got off a little bit. Okay, so this there's a 2019, there was a lot of noise made from Google, and I think their Sycamore system, it was a 53-bit quantum system on, hey, we've achieved quantum supremacy. And so that was kind of a moment in time we started tracking. Again, from all the vendors, we knew where they stood in terms of qubit counts, things like that. Well, it only took a few months before people said, well, okay, that thing you said could never be solved classically, turns out we can do it in 3 weeks. But that's kind of the beauty of science, and it's the beauty of the HPC community as well, to say, look, iron's going to sharpen iron here. We want to use HPC to help, accelerate quantum, but we're going to keep you honest at the same time. If there are other ways to solve these problems, smart people are going to do what they do. So from there, though, you saw everyone's expected trajectory as far as the qubit counts, and then you kind of see, where we're at on reality. There was another really important experiment that came out in 2024 that basically kind of proved some of the underlying principles of error correction. So great, awesome, need that, but it didn't magically solve everything. So you can see here Satoshi hit some of these numbers as well. It's like, look, the problems we have to overcome, first of all, is just, noise. So even to get to a good, stable physical qubit, you've got to solve a lot of those problems. And then I need the right error correction if I want to get to an appropriate number of logical qubits. And then finally, I've got to get to this scale. And so you've got Nobel Prize winning problems at each one of those steps. And so our lead researcher came over from the Google team several years ago. And speaking of Nobel Prizes, one of our collaborators, John Martinez, actually just won the Nobel Prize this year for some of his work based on this. So that's the class of problem we're still talking about here. Now, that being said, there may be a path here to actually getting some quantum advantage out of all of this. And we think the magic combination really is the right level of networking with HPC and AI and this development environment. If you haven't seen it yet, we've got kind of two things to follow up on. Kind of lay all of this out in great detail in a paper. It's how to build a quantum supercomputer. And we also have this group called the Quantum Scaling Alliance, kind of different members for each part of the stack that are trying to realize all of this. So those are two really good follow-up items to really go deep. But I will give you a sneak preview, and here's what we think a quantum supercomputer looks like. So you've got some amount of traditional HPC, and we think it's eventually, Dan, it's all going to be Ethernet based. You can forget that InfiniBand stuff. They're going to deprecate it, I promise you. So you've got a layer there. You've got another layer, kind of this quantum controller that's doing a couple of things. It's doing the error correction for you, and it's also doing the node control for the QPUs themselves. And as you can see, there are multiple layers of networking here, and each network has its own, kind of personality and unique needs. So that's why, at the end of the day, this is going to be, at this level, it's going to be a tightly coupled system. Now, is this your TAC supercomputer? Is it the LUMI supercomputer? Is it RECON? It may not necessarily be that one. Now, if you co-locate it, sure, but for running that QPU function, that quantum function, you're going to need this combination, okay? So if I leave you with nothing else, just kind of take that away. And again, we can go through more details why you need that tight integration. But there are definitely a lot of real-time constraints that are involved, especially on the node control, error correction. When you actually run a job on one of these quantum processing units, it's not just like you just load the job and it's done. It literally takes think of it like a state machine running, right? It's all based on probability. So you've got to run we call it a shot, you got to run that sample or that experiment, if you will, like 1 million times over, and then you get a sample to ultimately get then a prediction out of it. So it's not just a feed it, you get a little bit of data in, run it, a little bit of data out. You got to do that millions of times. So that's what I think kind of gets lost, and why you start to understand why some of this infrastructure is needed for the storage, for the telemetry, all of that. One little quick part. So let's, if that's the offense, let's talk a little bit of the defense here. So just for everyone's awareness, on the flip side of things is, well, okay, how do we protect all of these enterprise assets? How do you protect, your environments if that quantum machine is realized, and you're not, a lot of your code signing or single sign-on and all of that, if it's relying on algorithms that are not quantum proof, that's going to be a problem. And in fact, we have some government agencies that have helped us out with this, and so they have very strict timelines that are in place now for, if they're going to procure new things in this time frame by certain dates, it's got to be, you got to have provable saying, look, these things are quantum proof. Our plan right now is we'll offer up basically, both modes, meaning for whatever reason, if they're still concerned that the new quantum safe algorithm really isn't quantum safe, we'll still have the old ones to kind of fall back on. So that's at least our plan internally. Okay, and last but not least, AI after LLMs. So this is just another kind of, normally this would be just kind of a quick takeaway, especially for a lot of the enterprise customers. If you get too enamored with AI, you just think, oh my gosh, yeah, this is it. We're going to let a handful of companies decide everything when it comes to AI. Really, the point here is that, look, there are real practical limitations to what a large language model can do. And in fact, it's not the end state by any means. Amazing what they can do right now. Amazing what they can do, essentially simulating some level of reasoning. But that is not the end state for a lot of these reasons. There are some very practical limitations. Access to high quality data, right? We know that one already. So what do we do instead? We generate synthetic data, okay? Once we've consumed all of that, kind of what's next? What do I think we're going to see here? It's going to be consuming visual data. So that's where I think a lot of the physical AI comes in, just because of the information density. That's where the next big thing of training is going to be, is around visual-based data. And so that's going to drive a bunch of other stuff, through the roof expense-wise. Okay, the next one is just computational limitations. We all know the quadratic scaling problem, combinatorial hardness. That really then speaks into the inferencing aspect of all of this, especially as these reasoning models come online, as you explore more and more paths. The inference isn't just a simple kind of, look up and you've pruned the big tree. Suddenly the inference becomes, as computationally intensive as the training, and that's going to be a real problem. Other fundamental limitations, again, we've talked about some of that this week around the trustworthiness. I'm going to talk about the complex reasoning now. So quick takeaway here, you should just say, look, LLMs are not the end state. This is a great work done from the Apple team, actually last year. And so this is right when the reasoning models started to come online. And so they did some analysis. In this case, they used Claude. And what they found out was, look, for the simple cases, the reasoning model and the standard model actually do about the same. In fact, the language model actually outperforms in a lot of cases. And then you do get to this middle level of complexity where the reasoning model does really well. Again, very compute intensive. But once you reach a certain level of complexity, both just fail. I mean, it just makes stuff up, right? And that's a real scary thing for sure. So it just kind of underscores, based on real data, real analysis, that the reasoning models, as good as they are, at least right now, in kind of this mid-complexity level, again, it's not solved science. So just a couple more slides here. I'm going to leave you with another thing you can do some research on. And so how's the community at large looking at this? Our work is kind of focused in this space. So a psychologist, Daniel Kahneman, he won a Nobel Prize back in 2002. He has this simple model for how humans basically do decisions, kind of the framework around it. And it's he broke it down as, look, you're either system 1 or system 2. System 1, you operate automatically, quickly, no effort, no sense of voluntary control, it just kind of comes to you. System 2, okay, that's where it takes complex computation. That's where you really have to think, really build on all of your knowledge base, and that's what makes human a human. So kind of put it into system 1, system 2, you can kind of think, well, gosh, that's kind of what an LLM is, right? It just, it's just really doing that, basically that using probability and, just predicting what that next token is going to look like. And then for system 2, basically our premise or our work is saying, look, if we can augment this system, because it's actually pretty good, does a lot of things. We operate a lot of things where, just system 1, we don't have to think too hard about it. So there's something called an energy-based model that we think has a lot of promise. The community's also looking at this a lot. And the basic idea would say on a system 1 or an LLM type model, right, you're taking an input X and you're trying to, predict, well, what's the Y? What comes out of it? An energy-based model, you train completely differently. You do things in pairs with an input and an output, and you basically, from a training standpoint, you assign lower energy to a pair that connect, and you assign higher energy to something that you want to have divergence in. And I'm not going through today everything. The nice thing about this, you can see some of the benefits, but from a computation standpoint, turns out you can do these energy-based models just with CPUs. You don't need a lot of the intense linear algebra to do that. So that's why we think it has a lot of promise from the energy standpoint, and application, and can kind of bridge that gap on the reasoning side of things. So again, maybe another good topic for follow-up if we make some progress on it. And normally I'd kind of walk through this, but at the end of the day, that's where we're going to, we talk a lot about heterogeneous compute, and that's really kind of the idea. If you follow the line on the bottom is, ultimately, look, we're going to need all forms of CPUs, GPUs, FPGAs, other accelerators that come online in a way to, map functions to, the compute that best suits them. So we think ultimately that's probably the end state, and but there's a lot of work, between here and there. So I think with that, that's it.